In this video, we are going to discuss about flash ADC. So it is also called as parallel ADC. And here we are going to discuss about 3-bit ADC. So for 3-bit ADC, so here if I take this one as n, so we have 2 power n resistors and 2 power n into n priority encoder is required, then 2 power n minus 1 comparators required. Okay, so here if I take if I consider it as a 3-bit, you require 8 resistors, 8 cross 3 priority encoder, and then 7 comparators are required. So here this flash ADC is also called a simultaneous type ADC because within 1 clock cycle, that is within 100 nanoseconds or less than that one, it will convert my analog signal into a digital signal. Okay, so it is called as the fastest ADC. It is formed by the series of comparators. That is, it will compare my input analog signal with the reference voltage. Okay, and the output of the comparator is given to a priority encoder circuit, which will produce as the binary output. So the construction of this one is very simple and it is easier to design. What is the disadvantages? It is not suitable for ADC with more than 3 or 4 digital output bits, as the number of comparators get increase. So if you see for 2 power, that is for n is equal to 3, you require 7 comparators, means for n is equal to 4, you require 15 comparators, right? So the number of comparators get doubled, right? So it is a disadvantage. So this is my block diagram of the flash ADC. See here, if this or I can see I require 8 resistance, no? So if I take this is this 8 resistance value is 1 kilo. Okay, 1 kilo. Okay, so if I apply a voltage divider rule, okay, so what is this value? This is nothing but 1 resistance VR followed by 8 resistance, 7 resistance are connected in series, so it is 7k, right? This is 1k. So if I take this one as VA, okay, so what is my VA? According to voltage divider rule, VA is equal to my total voltage VR into 7k divided by 7k plus 1k, right? So it is nothing but 7 divided by 8 into VR. Okay, so I can write this one as 7 by 8 VR, right? So similarly, if you take this one, this is nothing, it becomes 2k, right? This becomes 2k for this one. This is 2k. So for this is VB, so this becomes 2k and this becomes 6k, right? 6k. So we'll get the answer as VB is equal to VR into 6k divided by 8k, right? So it is nothing but 6 divided by 8 by VR. So I can write this one as 6 divided by 8 into VR, and this one as 5 divided by VR by 8, and this one as 4 divided by VR by 8, and this one as 3 divided by VR by 8, and this one as 2 divided by VR by 8, and this one as VR by 8. Okay, this point. Okay, so this is my comparator. Okay, now this is my comparator. So I have connected 7 comparators, right? So I'm going to compare the input signal. Okay, the input which I am going to convert. So let me assume I'm going to convert my input signal voltage, that is 7 is my analog voltage, right? So analog input and the expected output, right? The V out must be 111, right? It's a digital value, right? So I need to convert this one into binary number, right? So I'm going to compare this 7 volt. Okay.
Yeah, that's and move. Make
So we know that whenever this V plus signal, okay, V plus signal is greater than V minus, V plus is greater than V minus, you will get V saturation, right? So whenever V plus is less than V minus, you will get minus V saturation, right? That is, this is a positive volt and this is a negative volt. Okay. So I'm going to take this VR as equal to 8. Since the denominator I having 8, so if I solve, I will get this is 7 volt, right? 7, 6, 5, 4, 3, 2, and 1. Okay. So what is the value I am having here? The positive is 7 and negative is 7. So you will get the output as 1. Okay. So here the positive voltage, this is 7 and this is 6, right? That is V saturation, right? So this output is given to a priority encoder. So it is nothing but 8 cross 3. Okay, so we have 8 inputs, I0 to I7, and ABC is my output. So the detailed video I will give it in the description box, and I0 is always connected to 1. Okay, so it can also be connected like this, right? By okay, by connecting another on comparator, right? Minus and plus, so the plus is given to the positive and the negative is given to, like this also you can connect. Okay, so here also you can see this is always 0, this is always 0, right? So this is always 0, so you will get the output as 1. Okay, so this truth table of the priority encoder. Okay, so whenever I0 is 1, you will get 000. Whenever I1 is 1, you will get 001. So whenever I2 is 1, so we don't want to consider what happens to I0 or I1. If I0 is 0 also, if I2 is 1, you will get the output as 0, 1, 0. So likewise, if I5 is 1, the priority is given only for the I5. So if I5 is 1, you will get the output as 101. If I7 is 1 means you will get the output as 111. So you can see here highest priority is given to I7, right? So the I7 is 1, therefore you will get the output as 111. Okay. So here if I want to connect instead of priority encoder, I can also use normal encoder. Okay, if I want to connect a normal encoder means you have to connect a XOR gate before this, right? So you have to connect a 7 XOR gate. Okay, so between these two um, circuit, this two output, you have to connect a XOR gate, and the output of the XOR gate is given to the I1. Okay.